Get started. So let's first do a brief review of the previous contents, right? So introduce the principal component analysis. So the principal component is actually a dimension that we want to find. And this dimension is a linear combination of the original features in the original data sets. So for example, in the original data sets, we use x1 and x2 as the features. Right, so the data, if we plot all the data points along these two features, it may look like this. And the thing with the original feature is that they may not be the best features that characterizes the most amounts of variance in data. So our task is to find dimension that can better describe the data, so that more variance is accounted or explained. So in another way, the data points should spread along that new dimension as much as possible. So we can find this new dimension by trials. Like we can try different angles. Like this could be our first candidate dimension, and we can see how much our data spread along that dimension by making projections of the data onto this dimension. And we can use the distance from the projection, from the projected position to the 0 points. So we can, so the distance can be measured, and the variance can also be defined based on the distance, which is basically the summation of the distance, the summation of the square of distances. So sum square, SS, short for sum of squares. So different angles, we can see that different angles of dimension will result in different SS. And our thoughts is that we want the SS to be as much as possible, so that the data points spread across the dimension more. So we want to maximize this this quantity, this sum of squares. So far we haven't talked about how we can find the right angle, the exact, the maximum, the angle that maximizes the sum of squares. But we will assume that we already know how to do that, and we will see that we will eventually stop at some point that this sum of squares is maximized. And we call this direction that this current dimension points to is the principal components, or PC1. Okay, so with these principal components, it can be described by a unit length vector. And it's this short vector just pointed to the direction of the new dimension. And perpendicular to this PC1 is PC2, which is the green direction shown by another unit length vector. So now we can use the PC1 and PC2 instead of the original x and y, the x1 and x2 to describe the data. So in this way, we kind of rotate the data points by, so that along the PC1, the data points express, the data points spread along to a larger degrees other than the original feature weight and wingspan. So now the thing with PC1 and PC2 is that how do we interpret these features? So what does PC1 means? So the meaning of PC1 is actually resides in the values of the U1, the unit length. So the unit length here, U1, we already see that it is how much, like 94.94 times x1 plus 0.34 times x2 tilde. So it's basically a combination of the weight and length. And these PC1s is basically a hybrid features rather than a single dimension, a single meaning feature. Okay, so and the advantage of using PC1 is that we can account for more variance than the single feature alone. Okay, so as we will see later, that's the principal components that we find among the data can be used to explain some patterns that is not identifiable in using the original features. Alrighty, so next let's focus on the question of how. Okay, we want to compute the principal component. So how do we compute the values of U1? That is the key problem we want to solve today. So I think we have covered this page last time, right? So we can define U as U1 and U2. So here we still use a two-dimensional data sets as an example. And if your original data has more than 2 dimensions, like 3 dimensions, 5 dimensions, then the corresponding principal components vectors, they also have the same dimensions. Okay, so now given the data points, x1 and x2 tilde, we can use the inner product to compute the length of projection. So we use the inner product between u and xi, okay? And because it is the summation of squares that we want to maximize, so we need to square that inner product, which results in these quadratic terms, right? A summation of a bunch of quadratic terms. And this term can be further described, can be further expressed by a matrix form. Okay, so now you given 2 by n x tilde matrix, and we multiply the 2 by n matrix with x tilde transpose, which is n by 2. Okay, so this thing in the middle, it's 2 by n times a n by 2 matrix, right? Which is a 2 by 2 matrix, and u transpose is a 1 by 2, right? And the u is a 2 by 1. So and the thing in the middle is 2 by 2. So dimension-wise, this equation is valid, right? And you can see that this whole thing, if you expand it, it will be exactly what this summation term indicates. Okay. So now we just want to maximize the summation, the SS, in the form of matrix representations. And we use an additional 1 over n term to normalize the whole thing. And remember, we need to have the constraints that the u is a unit length vector. Otherwise, there are infinite number of possible representations for that vector. Okay, so it's a very typical constrained optimization problem. So let's do some bit review here. We want to maximize some target function. This is our goal function, okay? And the constraints we face is in a equation, okay? It's not an inequality. So if, remember, in the SVM problem, the constraints, we have a bunch of constraints that are inequalities defined by the support vectors, which is associated with the alpha, right? Alpha is the Lagrangian we created. But for this one constraint, it's much easier. We can use the lambda as the Lagrangian multiplier, right? So let's expand this term in the middle a bit. Okay, so we are expanding these matrix multiplication term here. So we will look at the nature of this matrix multiplication first, right? So if you look at the first row of x tilde, so this thing is x tilde. The first row is just the normalized row of x1, right? We take the means of the first feature, which is mu1, and subtract it from each item, and divided by the sigma, which is the standard deviation for the first feature. And this thing on the left is just the transpose of x tilde, right? We just transpose the whole matrix. So now if you focus on this term on the right, the left corner, the upper left corner here, it is the summation of a bunch of squares, right? So how do we compute these left upper upper left corner is that we take the first column and conduct a dot product with the first row. Okay, because the first column is just the first row itself, right? There's no difference. We just make the whole row a column, right? So it's just a summation of squares. And if you look at the second column, if you look at the upper right term here, now it's a bit different. It is the summation. It is a summation of x1 minus the mean of the first feature, and x2 minus the mean of the second feature. So it's actually the second column conducting a dot product with the first column. Okay, so we have names for these terms, and the first term is what we have known. What we are better familiar. We are more familiar with the first term. It's just the variance of the first feature, right? It's the that's how we define the variance of one feature. And so is the bottom right corner, this item within the green box. It is the variance of x2. And what's trickier part is these blue parts. And we give them names, the covariance between two variables, because it is the difference from x1 to its mean times the difference from x2 to its mean. So it's not the variance of one variable, but it's the covariance of two variables. It basically measures how the two variables are related. That is how they move towards the same direction. Okay, so the larger covariance means that the larger positive. So the covariance can be positive or negative. If it's a positive value, that means the two variables change in the same direction. So anyway, given a 2 by m feature matrix, the results of x times x transpose is a 2 by 2 covariance matrix. So now we need to remember this term, covariance matrix. That is how we use the term to describe this matrix product. So we can sometimes denote it by this sigma, and but here in this case, because we use the larger sigma, the bigger sigma inside, so it's going to cause some ambiguity. So why not we just call it the covariance matrix? Okay. So now back to the optimization problem. Now we need to use Lagrangian multiply method, right? We need to define an extra variable, lambda, okay, and to construct the Lagrangian, okay. Now we convert the constraint optimization problem into an unconstrained Lagrange optimization problem. So this L is our new target function that we want to maximize. Oops. Oh. So this L, capital L, is something new that we want to optimize. And it is just the original target function minus lambda times the constraints. That is our constraints. So we just move the 1 to the left. So it becomes the norm of u minus 1. Okay. So we, having lambda included, we have this Lagrangian constructed. So because it's the L function we want to maximize, we just need to take the derivatives of L with respect to our target variable, which is u, right? So now here we have some more tricks about the matrix multiplication and how to take the derivatives. So the basic principle, to put it simple, is that we can treat the matrix as if it is a constant scalar number. Like the case here, we can treat the u transpose times u as if it is a quadratic term. It is as if it is a variable u times itself, u squared. So the results of taking the derivative of this function is that we have only one term, lower order term u left. And on the right, we also have the same thing, because inside it is u times u. So there's only one u left if we take the derivative of u. So we want the derivative to be 0 because it is the maximum points that we want to find, right? So this whole equation needs to be 0, and we can solve it as if it is a linear function, right? So we have a bunch of things on the right. It is on the left, it is the covariance matrix times the u equals lambda times u. Okay, so it's just it becomes a a set of linear equations we can easily solve. And there's a special name about this linear equation. It is the solution u is the principal eigenvector of the covariance matrix, and the corresponding maximized sum of squares is a corresponding eigenvalues to those eigenvectors. And actually, this equation in the blue box here, it is just exactly the definition of eigenvectors, okay, of a matrix, of this covariance matrix. Okay, so now let's get a little bit review of what eigenvectors is. It is something we picked up in linear algebra, right? In as some preparation knowledge maybe years ago. Okay, so maybe we need some refreshment here. All right, so eigenvectors, it's in German or Dutch, it basically means my vectors. So it is describes the basic characteristics of a matrix. So it is defined in this way. So given a square matrix A, okay, the number of rows and number of columns should equal, and the column vector V. Then if we have the square matrix times the vector equals some constant lambda times the vector itself, then we say the V is the eigenvector or characteristic vector of A, and the lambda is the eigenvalues. Okay, so I think the meaning my vectors in Dutch probably refers to the fact that no matter how like A times V, the V is a transpose is a transformation of V, right? But that doesn't change the direction of V. It just applies a constant multiplier lambda to V, right? The result of A times V doesn't change the direction of V. So that is basic. That is why it's called my vectors. It is something that doesn't change. That's something inherent to the matrix A itself. Okay. So yeah, almost all vectors change directions when they are transformed by A, except for those eigenvectors. So let's see how eigenvectors can be solved. All right. So basically, well, let's first look at some properties of the eigenvectors and eigenvalues. There's a theorem called spectral theorem, which basically says that if the matrix A is symmetric, which means after we transpose it's itself. So all the elements are symmetric along the diagonal line. And also, then if the the matrix A is symmetric, then A is orthogonally diagonalizable and has only real eigenvalues. So that means there exists some real numbers from lambda 1 to lambda n, some eigenvalues, and they are orthogonal, which means those vectors, if we take any of those eigenvectors, their inner product is 0. Okay, so that is a very important property that we're gonna utilize. Okay, so now let's take one more step towards our goal, because remember, in our previous settings, we actually want to find the eigenvectors and the eigenvalues of the covariance matrix. So it's a very special type of matrix. First of all, it is a symmetric matrix because it is the results of multiply x with x transpose. Well, it's x tilde, it's normalized, x tilde times x tilde transpose. And the result of that product is a symmetric matrix, okay? So in the case, now we generalize this situation a bit by looking at a matrix with m by n dimensions. So the result of A times A transpose is m by m, and the result of A transpose times A is n by n. So they have different dimensions, but they were both symmetric. Now let's look at their eigenvectors. And from this spectrum theorem, we will know that the two matrices A times A transpose or A transpose times A, they actually, it's interesting, they actually have the same non-zero eigenvalues, okay? So we can simply prove this. So for example, we let the vector V to be a non-zero eigenvector of A transpose times A. Right? We assume that V is a non-zero eigenvector. So we would have that by the definition of the eigenvector, we would have that A transpose times A times V equals lambda times V, right? So we can simply multiply the both sides with another vector or another matrix A on the left and on the right, right? We would have something like this. Then we use the rule of association by putting A times A transpose together, and we would have some new vector here. On the left and right, we have some new vector, A times V and A times V. So these two would be the new eigenvector for the matrix A times A transpose. But notice that the lambda doesn't change. The lambda exactly the same lambda here, right? But the matrix are different. The matrix in the blue box is A times A transpose. And here in the blue circle, it is A transpose times A. So although they are two different matrices, but they share the same eigenvalues, okay? And that makes things easier because we know that the shape are different, A times A transpose or A transpose times A, depending on M or N. So for example, when your M is very big, right? So that's not easy to solve the eigenvector problem for a M by M if M is very big. But if you happen to have very small n's, right, then you can simply use the alternative way. You can refer to the other matrix, the other covariance matrix, which is A times A transpose. That has much smaller dimensions. It's just n by n. So in this very extreme example that I'm showing here, say if your A is a 2 by 500 matrix, so it recalls our example, right? If our data set is like this, we only have 2 features, but we have 500 examples. Then the quick way to find the eigenvalues for a 500 by 500 matrix, which is from A transpose times A, is to first find the 2 eigenvectors for this 2 by 2 matrix, A times A transpose, right? Because the results of A times A transpose is just a 2 by 2 matrix. And what about the other 498 eigenvalues? They are zeros. Okay, so that's an interesting property because the results of A times A transpose is just a 2 by 2 matrix and it's symmetric. And by spectrum theorem, we know that a 2 by 2 symmetric matrix would only have 2 positive or 2 non-zero vectors, and they have 2 non-zero eigenvalues as well. And these 2 eigenvalues are just the 2 non-zero eigenvalues in the 500 by 500 matrices, and all the other vectors and eigenvectors are eigenvalues are 0 eigenvalues. So that's a really, really helpful property to us. Okay, so now going back to the a more concrete problem here. So when our x, the data x is 2 by m, right? Now we can construct the covariance matrices. It's a 2 by 2 matrix, regardless how many m's you have, right? As long as you use x tilde times x transpose, then all the dimensions reduce to 2 by 2. And we know that it is a symmetric 2 by 2 because the lower left is a covariance between x1 and x2, and the upper right is also the same term. Okay, so that means there are only 2 eigenvectors and 2 eigenvalues, right, which satisfy these 2 equations, right? The covariance matrix sigma times u1 should equal lambda 1 times u1, and assume that lambda 1 is the bigger one among these 2. Okay, then we can define the total variance in data by lambda 1 plus lambda 2, and the PC1 mu1 actually accounts for that many, lambda 1 over t, which is lambda 1 over lambda 1 plus lambda 2. That is the proportion of total variance that PC1 can actually account. Okay, and PC2 accounts the remaining variance. Okay, so it's a very simple linear relationship. So of course, that means the larger eigenvalues means that principal component is more important in terms of describing the amount of variance described within the data sets. Okay, and in a more generic case, if we have n by n, and it easily extends this whole concept. The result covariance matrix is n by n. It's also symmetric, right? If you look at the entries, right? Just you take it along the diagonal lines. So x1, the covariance between x1 is here and also here. The covariance between x2 and xn is also here. So it is symmetric. So the results will be this time there will be n eigenvectors and non-zero eigenvalues, right? We would have more equations satisfied in this way. And let's lambda 1 to be the biggest one, okay? And we sort all the lambda values in a decreasing order, in a descending order. So the total variance is a summation of all the lambda values, and the amounts of variance accounted by PC1 is also the ratio of lambda 1 over the total accountants of the total variance. So in this case, we will find that not all the principal components are equally important, because only the first few principal components account for the majority of the variance. And for the later parts, say if you have 100 principal components, maybe the rest of the 90 principal components, they only account for maybe 1% or 2% of the whole total variance. And that means they are not useful in describing the data. That means we can toss these not very important principal components by reducing the dimension to only the first few to the dimensions defined by the first few principal components. Okay, so now we can roughly have some idea of how dimension reduction is done. All right, let's further proceed on to the next slide. All right, so in Python, it's quite easy to solve the eigenvector and eigenvalues using the NumPy package. So for example, we define the x as a 2 by 6, 2 by 5, 2 by 6, right? So now we can just use the linear algorithm module, and there is an eigenvector function, function, and we call that eigenfunction on the covariance matrix. So covariance matrix is something you need to construct yourself, right? You simply use the dot product between the matrix and its transpose. So you will have the eigenvalues and the eigenvectors returned separately. Okay, if we print the eigenvalues and eigenvectors, it will be like this. So the interesting about eigenvector is that they are orthogonal, because by spectrum theorem, your input matrix is symmetric. So the eigenvectors, they are orthogonal. So if you compute the dot product between the two eigenvectors, it will be 0. And more interestingly, the first eigenvector value, it is very big compared to the second one. Okay, so now if we apply the notation of the variance explained by the first principal component is almost 386 plus over 386 plus 74. So that is a vast majority of the variance. Which says the first principal components almost explains all the variance of the total of the within the data sets, and the second principal component is actually not that important in describing the data sets. Okay. Yeah, that's a very simple example here, and now let's go one step further to really conduct some dimension reductions by removing by only keeping those important dimensions that we want. Okay. Alrighty, and I think it's quite straightforward. So continue from the previous content, we will have the covariance constructed and all the eigenvalues, eigenvector and eigenvalues computed. And what we need to do is to simply select the top k eigenvectors, okay, from U1 to UK, right? And we also remember keep their eigenvalues from lambda 1 to lambda k. Okay, so now if we put all these k eigenvectors, combine them into a matrix, right? We call it capital U. Then we can use this capital U, it is an n by k matrix, to cast. It will be a tool to cast the original data sets into a k-dimensional subspace, because the original data is in n-dimensional data space. Now, if we select only the k PCs, the top k principal components, then we actually select the k dimensions to be left. Okay, so we can simply, for example, given the data points x tilde, we can project x tilde into this subspace by multiply the U matrix with xi. Okay, if we put U transpose on the left and x tilde is a vector on the right, because U transpose is k by n, right? And xi is n by 1, so the results would be a k by 1. Okay, so we only have k items left, which is the coordinates for x tilde I in its is the coordinates of xi's projection in the k-dimensional space. So we use a different name. We use y from y1 to yk, and these are the projections in the k-dimensional space from x tilde. Okay, so we project x tilde in the high dimensional space to y in the low dimensional space. Okay, and if we have a bunch of examples, say we want to project all the m examples, then we can easily do that by multiply U transpose with capital X tilde, which is the matrix, which will result in a k by m matrix. And this capital Y is actually the collection of all projected data points in the low dimensional space. Okay, so by this step, we can successfully reduce n dimension data into a k dimensional space. Okay, and this reduction is commonly used if we select very small case like the first 2 dimensions or first 3 dimensions for visualization, right? Because we cannot visualize a 4-dimensional data sets. And so, for example, in the case of word embedding studies, after we have trained the very large, after we have trained an embedding model that returned the embedding matrix, which is usually 300 by some 10,000 word vectors, then we can easily reduce it into a 2-dimensional space by applying a PCA analysis. And those 2-dimensional space would be much easier to visualize. For example, we can plot the coordinates, plot the word of queen and the king by their 2-dimensional coordinates onto the 2D space, right? And we can draw the connections. So yeah, so this is a very really really neat, really simple and elegant way to reduce dimensions. Okay, and of course it comes with a cost. It comes with a price because we removed some unimportant principal components. We only select the top k, and the rest of the n minus k principal components, they are removed. So there, in theory, there's some loss of information. Okay, but if we we will find that if we select the k to a relatively bigger value, say the top 10 dimensions maybe, then the loss of information is quite small. Okay, so now let's look at another some technical details. Okay, so the covariance matrix of the transform data, let's look at it. It's quite interesting. So the y is the transform data. Remember how we get y, right? We get y by u transpose times x tilde. And we can compute the covariance matrix of the transform data. So now it's time. Now this is in a lower dimensional space, in a k-dimensional space. Excuse me. So by the definition of covariance matrix, it is y times y transpose. And we substitute the y with u transpose times x tilde, right? And this also u transpose times x tilde. And again, apply one more transpose here. So we actually turn back into the covariance matrix of the original data sets with only ut and u on the left and the right. Okay, so this will result in a diagonal matrix with eigenvalues as the diagonal elements. That's a really interesting results, right? So all the variance, all the covariance in y, if yi and is different from, if I is different from j, then the 2 different dimensions in the y space, in the transformed data low dimension space, they are 0. So that means all the transformed new dimensions, they are orthogonal towards each other. That is the property of the transformed data sets. Okay, so if we look at the 0 transformation, or look at the covariance matrix and the shape of the data, a 0 covariance data set means that there's no direct correlation between the 2 dimensions, right? On the left, the covariance between x and y is very small, almost 0. So all the variance is basically along this y-axis. But if the covariance is big, then it will shape it will shape some angles, and that means the original dimensions are not very well representations for the original data sets. Okay, and that means if the covariance between dimensions are 0, which means they are all independent features. Okay, so far, yeah, we have covered. We have talked about how to obtain the eigenvectors, eigenvalues to conduct the PCAs. And in practice, we'll have a faster numeric method for finding the principal component analysis, for finding the principal components. So it's called singular value decomposition, or SVD. Okay, so SVD doesn't work on the covariance matrix X times X transpose, but it works on X directly, and it decomposed your matrix X by into a product between 3 matrices. The first U is a unitary matrix n by m, and the one in the middle is n by n, but it's a rectangle diagonal matrix, and the diagonal values are called the singular values. And on the right, it's an n by n unitary matrix. So the relationship between SVD and the eigen decomposition, eigenvector method is that the singular values in the sigma is actually the square roots of the eigenvalues, and the U is just the results, the principal directions we want to find, the U transpose. So the relationship from here to here can be easily inferred, because it's just the transpose of matrices and the matrix multiplications. You will find that the singular diagonal matrix is just the eigenvalues that we need to find, the square root of eigenvalues. So in Python, the priority choice is to use SVD. SVD has a much faster implementation than finding the eigenvectors. But in theory, they are actually can be the vectors found from the SVD is actually the same as those found from the solving eigenvectors. Okay. So far, let's do a little bit recap here. The procedures to perform PCA is to first normalize the data by subtracting the mean values and divided by the standard deviations. And then we want to find the eigenvectors and eigenvalues for the covariance matrix. And ideally, preferably, we want to sort the eigenvectors by their eigenvalues. And then we can observe whether a small number of eigenvalues are much bigger than the others. And those will be our top k elements to be selected, top k dimensions to be selected. And in that way, we can reduce the original dimension in the n dimensional space to a k dimensional space. And then we can interpret the principal components, like which ones are the most important. Okay. And next, let's quickly go through some applications of PCA. So the first function of PCA is to gain better interpretation of the original features. Okay, so use the example here, the bird database again. We have length, wing, span, and the weight as the original features, and the birds, right, as the data instances. So the X is 3 by 100 data sets. Then we can compute the matrix, the covariance matrices, and solve the eigenvalues. Right? We can easily find that the top one, the top two, actually they correspond. The top two eigenvalues, they are the vast majority of the total variance. So we can basically use the top 2 features to explain the data, And if we look at the first principal components, the vector here, eigenvector, tells us that this PC1 is 0.22 times length and 0.41 times wingspan, right, and 0.88 times weights. It basically captures the size, right? All these quantities are positive. And we can notice that there are some negative values here. The PC2 is the length plus wingspan minus weight, right? So it probably describes the kind of the stoutness features, right? Because the negative coefficients along the weights dimension. So we can basically explains the variance among data sets by inventing new concepts by looking at the coefficients of the principal components. Okay, so that is the first application, and of course the other applications are very apparent. We can use PCA to reduce the dimension for visualization and the data compression, right? If we use less dimensions from n dimension space to k dimension space, then of course it saves storage space for storing the data sets. And sometimes we can pre-process data sets by reducing its dimensions before feeding into some supervised learning models, which may result in almost for sure will reduce the amount of computation needed because you are using lower dimensional data, and it may potentially lead to better, more efficient models that doesn't lose any predictability, but using much cost you much smaller computational resources. Another famous example is called Eigenface. So the eigen, by looking at the principal components of the bunch of a collection of face images, we're able to conduct face recognition algorithm really quickly. So let's look at that example real quick. Say you have a training set of n faces, and each face is a black or white image by 100 by 100 dimensions. So we can flatten each image into a 10,000 long vectors, right? And assume that we'll stack them into columns, and we will have a large matrix, 10,000 by n, right? It's normalized, just like the bird data sets. So we can compute the eigenvectors and eigenvalues of the covariance, right? Which is of shape 10,000 by 10,000, okay? And each eigenvector is a 10,000 by 1 eigenvector. So now we can reshape the eigenvectors back to 100 to 100, right? Back into a matrix. So it's can be seen as the also a face image, which is called eigenface. Okay, so these eigenfaces can be used as the base. They are the base vectors. They are orthogonal towards each other. So they represent the abstract face space, and they can be used to represent any new faces by projecting. So given a new image, a face image vector, we can project it into a subset of the eigenfaces. And the projections, the new coordinates in that subspace can be used to identify whether this new space, whether this new face exists in the original data sets or not. Okay, so in practice, we don't need to keep all the 10,000 eigenfaces. And luckily, we just need to use 100 or 150 eigenfaces to conduct face recognitions that are sufficiently good. So that is the amazing place of these methods, because we kind of reduce the dimensions from 10,000 to only 100 which saves us huge amount of computation time, right? So if you visualize the first eigenface in the face dataset, it looks like this. So it may tell some main features along layouts on your face, like the shadows in the hair, like the little shadows on the cheek, and all the eyebrow, the eyes positions. So it's a interesting experiments. And in our assignments, we will conduct something similar to this Eigenface study, but using other different data sets. So I guess that's it that's all for the PCA chapter. And I think I can release the assignments some point this week, and you can start work on it. It's a really interesting Eigenface experiment like this Eigenface.